morning everyone. I am Dr. Dwivedhi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. I am in the process of delivering the lecture on the course Aircraft Stability and Control. Today I am in the lecture number 59, which covers definition and terminology, which is linearization of aircraft equations of motion. In this, I am going to discuss about some terms. These terms are related to the module 4, in which we try to make equations of motion of the aircraft in a linearized form so that these equations can be solved very easily by using algebraic form. In this process, I am starting here the first definition and the terminology, which is perturbed flight. What is the meaning of perturbed flight? That is the first term. So, in linearization of the aircraft equations of motion, begin with consideration of perturbed motion. Perturbed motion flight is defined relative to a steady state trimmed flight condition using a combination of steady state and perturbed variable for aircraft motion parameters and for force and moments. So in this, what is the meaning of the perturbation? Assume this aircraft is flying with a steady state flight. Due to some gust, a additional gust has come and aircraft has turned its, so it is very minor deflection of this motion, the direction of the motion. If the velocity is 100 and it's 2%, the velocity has changed. So this change, a small amount of change, is called the perturbation. So by this perturbation, we are going to solve the equations of motion, which are very complex and they are difficult to solve in the normal way. So perturbs are used to give a small deflection and then we have to calculate. Next term is speed damping derivative. These derivatives are used to indicate how much speed is damped during the dynamic motion or during the dynamic stability of aircraft analysis. It represents the change in drag coefficient CD with respect to change in U by U1. Its value is depend on the Mach number. So here the speed damping derivative, which you can see that it is a dCd U by du by u1. So this is called dCdu and this is called the speed damping derivatives. Okay, so these parameters are very useful to understand whether the system is dynamic stable or not. Okay, so these are used for this purpose. Now I have to discuss about earth axis system. We have different axis systems: earth axis system, body axis systems, stability axis system, and but first I am going to discuss about earth axis system. In this, the earth axis system is fixed to the earth with its z-axis pointing to the center of the earth. the x-axis and y-axis are orthogonal and lie in the local horizontal plane with origin at the aircraft center of gravity. Often the x-axis is defined as the north and the y-axis is defined as east. So I am just explaining here. This is the point of, so in this, if you see, this is the north and this is the east, and this is pointing towards the earth center. Okay, and this is the CG. So in this configuration, the x-axis is towards the north and y-axis is towards the east. E is for east and this is the north. Okay, so in this way we can define the earth axis system, and this earth axis system is also called the inertial frame of reference, because we assume for aircraft that the rotation of the earth is very minimal comparing to the rotation of the aircraft. So we can assume that earth center is the inertial frame of reference. So this next is Mach-Tuck derivative. This Mach-Tuck is a very important parameter, and in this, as per the speed of the aircraft, when speed reaches towards the sonic regime, the nose is trying to come down. This phenomena is represented as a Mach-Tuck. So Mach-Tuck derivative, that is Cm1, is the steady state aerodynamic pitching moment. It will be non-zero for cases where thrust pitching moment must be counteracted by an aerodynamic pitching moment to trim the aircraft to a total pitch moment of 0. For other cases such as glider and power of flight, Cm1 will be equal to 0. So if there is no power, then this Mach-Tuck derivative, that is Cm1, will be 0. So it will be non-zero for cases where thrust pitching moment must be countered by the aerodynamic pitching moment. So you can see this, that this is the aircraft. This is the aircraft. So here, this is the CG and this is the AC of the aircraft. So this lift is supposed to act at the AC, and this lift will, and this is the distance between this you can say as X CG. So there will be a pitching moment which is trying to rotate in this direction. You can say that this is the Cm lift I am writing. But if you have an engine, and if engines are not fitted at the center of gravity, assume this is the engine point, here I am writing E. This engine, if producing like this, so this thrust T into this vertical distance, assume it is a Y. So this Ty will try to make nose up, and this is the nose down. So these two derivatives of aerodynamic forces, lift and here is drag, and here also weight and thrust. So this moment of this all things, with respect, it should be countered. And if it is here L into XCG is equal to T into Y. If this is okay, then this is a balanced and aircraft is stable. So this Mayak-Tuck derivatives are used to find out this type of criteria. Inertial axis system. The previous slide we have discussed about Earth axis system, and in the real field, in the real scenario, in the solar system, we can assume that Sun is only the inertial frame of reference. But when we consider the aircraft motion, we can assume that Earth is also stationary and Earth is also not moving. So inertial axis system is defined as the frame of reference system which is fixed. There is no motion at all. Earth axis system is generally considered as the inertial axis system for the aircraft movement, for the automobile movement, but not for space launching vehicles. Space launching vehicle, we have to assume that Earth rotation is also to be considered. So here, for normal cases, we can say that Earth is inertial axis system. Now, next topic is roll damping derivatives. So, this is one of the derivative of dynamic stability which represent the dynamic condition during the roll. It represents the change in rolling moment coefficient with respect to non-dimensional roll rate and is usually negative. So here, change in rolling moment. So dCl divided by non-dimensional roll rate. So roll rate is R. Okay. So this is called the roll damping derivative. Okay. It is important factor for lateral and directional dynamic stability. Okay, so in this case, we have to understand that the ratio of rolling moment coefficient with the ratio of the non-dimensional roll rate is negative. If it is negative, it means what? Dou CL by dou R is equal to negative means less than 0. If this is the less than 0, it is a dynamic stable. Okay, so in this way, we have to see that it is working properly. So we have covered here two axis system. One is Earth axis system, another is the inertial axis system. Next is the stability axis system. The stability axis system is rotated relative to the body axis system through the angle of attack. This means that the stability x-axis points in the direction of the projection of the relative wind onto the xz plane of the aircraft. The origin of the stability axis system is also at the aircraft center of gravity. The y-axis is out the right wing and coincides with the y-axis of the body axis system. The z-axis is orthogonal to points downwards in accordance with the right hand rule. So I am just explaining here stability axis system. So if I take the aircraft, first I will make the body axis system. This is the center of gravity and this is the x, this is the z and this is the y, this is the x x body axis. I am writing B here, so it will be very much clear. And this is the ZB. This is the body axis. Now, if we can make, I am making a dotted line. This perpendicular to this is ZS. This is the ZS, and this is the XS, and YS is equal to YB. Both are in the same direction, and this is the angle here, alpha. This is the angle of attack, alpha. So here it is very much important, and this is very good axis for wind tunnel testing. Once we use the wind tunnel, our direction of the flow will be facing XS axis. Always in this direction. Your flow will be in this direction. This is the V infinity. Okay, so for the experimental measurement for wind tunnel testing, this stability axis system is very much used, and after that we have to transform into body axis system or in the inertial axis system after getting the result. Okay, so this stability axis system is very important. We can see here, if the aircraft is flying like this and wind is in this direction, so this angle is called the angle of attack. So the forces and the moments we have to take with respect to the stability axis system, and after that we have to convert this stability axis system to the body axis system, and from there we can convert to the inertial axis system, because Newton's law only applicable for the inertial frame of reference. So the derivation of the equation of motion are on the inertial reference frame. So we have to transfer other axis system to the inertial reference frame. Then only we can apply the Newton's laws of motion. Next we have to see about the roll helix angle. This is also one of the very important parameter for lateral and directional static stability analysis, and this gives the absolute value of change in angle of attack alpha at the wing tip due to roll rate PB by 2U1 is called the helix angle. It provides the basis for the form of non-dimensional approach. So here the change of angle of attack and the roll rate PB by 2U1 gives the roll helix angle. What is the dynamic stability? Dynamic stability is concerned with the time history of the motion of the vehicle after it is disturbed from its equilibrium point. So here in this case we can see that if we disturb any object, there is a time t. Initially it was here. Due to some disturbing force, this point 1 has changed to here, and this is the time here. And if it is coming like this, going like this, slowly it is after certain time, if it is coming to its original point 1 in the same, then we can say that this is a dynamic stable. So this time is important, how much time it is taking to stabilize or destabilize also. Next case, if it is disturbed from here, it is going like this, slowly it is increasing like this, further increasing like this, it is a dynamic dynamic unstable. And if it is disturbed in the position and it is maintaining the same condition after time, then we can say that this is the neutral dynamic stability. Okay, so like this we can define that dynamic stability will always depend upon the time. So with respect to the time, if the amplitude is decreasing, it is dynamic stable. If amplitude is increasing, it is a dynamic unstable. And if it remains in the disturbed position at all the time, we can say that this system is dynamically neutral stable. Okay, next is cross derivative. It represents the change in yawing moment coefficient about the z-axis because of a non-dimensional roll rate. This CNP is also called the cross derivative. So here this you can see that dou NA by dou PB by 2U1 is equal to dou CN QSB divided by PB by 2U1. It is a CNP. This CNP is called the cross derivative. So cross derivative means if it is the yawing, it will be also corresponds to the rolling. So this rolling and yawing will be each other cross coupling. That is why it is called the CN. N is a your yawing and P is a pitching. So yawing and the pitching both are here cross coupling. Next is the Mach number. A number representing the ratio of the speed of the object to the speed of the sound in the surrounding air or medium in which it is moving. So it is a non-dimensional number. This number gives the velocity with respect to the speed of the sound. And if it is m1, it is a supersonic. Less than 1, it is a subsonic, and if it is greater than 1, it is a supersonic. Okay, and in between 0.8 to 1.2 is called the transient Mach number. Okay, so now primary control derivative, it is the next term, and these all terms are very much used in the perturbed equation of motion. So primary control derivatives, it is change in coefficient of lift CL with change in aileron deflection angle. This is also called aileron power. So here what happened, if you deflect the ailerons, it is, you assume it is a phi. So if dCL coefficient of lift and how much change in phi, so this is called the aileron power or primary control derivative. Okay, so this next is the roll damping derivative. So this derivative indicates how much the aircraft is able to damp the roll motion. It represents the change in rolling moment CL. Here CL is rolling moment. With respect to the non-dimensional roll rate, it is a P and is usually negative. This roll damping derivative CLP, it is shown here, this is the CLP. This CLP is the ratio of the change in CL and change in non-dimensional roll rate, this PB by 2U1. And this CLP is called the roll damping derivative. that opposes the direction of the roll rate. So this usually this CLP is less than 0. It means it is negative and opposes the roll produced by aircraft. So like this, every damping derivative, primary control derivatives, MACTAC derivatives, all derivatives indicates that aircraft is dynamically stable or not. Okay, so this damping derivative try to damp out the rolling of the aircraft when the roll rates are applied. Now, effect of wing angle of attack due to roll rate P. So here this vertical velocity due to roll rate changes the angle of attack at the left and right wing. If you see the left wing and the right wing, the angle of attack is different. For a positive roll rate, an increase in angle of attack is experienced on the right wing and a decrease in angle of attack is experienced on the left wing. An increase in lift on the right wing and a decrease in lift on the left wing. This you can see here. This is the diagram here. This is the left wing. So what happened here? This is your velocity u1, and here on the left wing, it is the flow velocity is downwards. So here, if you see, this is your alpha, and this alpha is negative here. Here, this alpha is negative. So your delta alpha lift at the tip is minus PB by 2u1. And if you see here, this side is upward, the velocity is upward. So if the velocity is upward, this angle of attack is positive, and here angle of attack is negative. This positive angle of attack will give PB by 2u1. Due to this positive angle of attack, the lift will be more in the right side of the wing, and at the left side of the wing, the angle of attack is reduced and lift is reduced. So this is the effect of the wing tip angle of attack due to roll rate P. So this P has got the effect on the wing aerodynamic forces like lift and the drag also. So if the lift is increased in the right wing will also have the more drag, and aircraft will try to turn in the right direction. In this case, okay, whenever in this and in this, so a moment will be also generated, and this moment will try to make the nose towards the right wing. So these are the references. That is Robert C. Nelson, Aircraft Stability and Automatic Control, NPTEL lecture of Aircraft Stability and Control by Professor A.K. Ghosh, IIT Kanpur. This is the reference. You can log in for this case. And thank you very much for joining the class. Next, definition and the terminology, which is related to the dynamic stability, I am going to discuss in my next class. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.